Hello, so today we're going to be taking a look at question 3 from the 2024 Chemistry Olympiad. So let's get started. There's a bit of context here. I don't think you need to read this really, but we're going to focus on the first question. So question A, determine the molecular formula of cyclopropane. They've given us the formula, so let's just draw this out. The skeletal formula, and then we know that each carbon's forming 2 bonds to other carbons. Each carbon's going to form 4 bonds in total, so it must form 2 other bonds to hydrogens, and that gives us our molecular formula of C3H6. So a nice simple start to the question. Now we're on to some thermodynamics. They're talking about a quantity called ring strain. You don't really need to know anything about it to answer the question. All we need to do is firstly write the equation for combustion of cyclopropane. If you've done Hess cycles before, you'll know that we're talking about complete combustion in this case. So we're going to be forming carbon dioxide and water, and hopefully you can all balance this equation quite quickly. There's 6 hydrogens, so we're going to have 3 waters. Now there's 6 plus 3, that's 9 oxygens in total. Part 2, calculate the enthalpy of formation. Well, this is a pretty standard Hess cycle that you find on an A-level paper. We have our starting materials here and our combustion products. We know this value, this is the enthalpy of combustion, and we have that here as for cyclopropane being minus 2091 kilojoules per mole. And then if we complete a Hess cycle, I'm just saying these are elements here, I don't really care what they are. Obviously the enthalpy of formation of oxygen is 0, so the only thing here we care about is the enthalpy of formation of cyclopropane. And here we got 3 times the enthalpy of formation of carbon dioxide, 3 times the enthalpy of formation of water. So if we complete the cycle, and the idea with these Hess cycles is that the enthalpy change is going to be irrespective of the route taken. So we can either take this direct route, or we can take this route and then that route. So we're going to equate these routes to each other. First route, and then we're forming carbon dioxide and water here. So 3 times the enthalpy of formation of carbon dioxide, which is here, minus 393.5 kilojoules per mole. Enthalpy of formation of water, minus 285.8, and then minus the enthalpy of combustion, since we're going the other way. So we've been told that's minus 2091, and if you put this into your calculator, you'll get plus 53.1 kilojoules per mole. Part 3 asks us to calculate the enthalpy of combustion per mole of carbon atom for cyclopropane. Well, there's 3 carbon atoms in every cyclopropane molecule, so if we've got minus 2091 kilojoules per mole of cyclopropane, well, per mole of carbon atom, we're going to divide that by 3, and that gets you minus 697 kilojoules per mole. Likewise, part 4, cyclohexane, well, it's C6H12. You don't actually need to know how many hydrogen atoms there are. Hexane, you should be able to tell there's 6 carbon atoms. Again, because there's 6, we're going to divide the enthalpy of combustion per mole of cyclohexane by 6. We're told here it's minus 3,951, so we're just going to divide that by 6. If you put that into a calculator, you get minus 658.5 kilojoules per mole. And yeah, so you can see it's fairly similar between the two, as you'd expect. So now onto some organic chemistry. Again, this part, context, you don't really need to read it, but this next part is actually very, very important for the entire question. So I guess the skill in this paper is really which parts are important to read and which ones aren't. So instead of highlighting the whole thing, the most important bit here is talking about the alpha carbon. And this is the most acidic carbon, basically, in a carbonyl compound. So if I have this, these would be the alpha carbons, this would be the beta, the next one would be the gamma. But the most acidic carbons are here. So when you'll see in the rest of this question, if we're thinking about deprotonating, we want to think about deprotonating one of these carbons, so losing one of these hydrogens, basically. So here, one of the alpha carbons has been deprotonated, as it says, and this form is an enolate. And the first question about this enolate is drawing a resonance form. If you've never heard of resonance forms, you're going to find this quite difficult. A brief overview is, well, the most famous, probably most famous, resonance forms are the benzene ones. Basically, we're saying the overall structure of benzene, the actual structure of benzene is a mixture of these 2 resonance forms, and we can interconvert these 2 structures by drawing some curly arrows. And so the overall thing actually looks a bit like this, which is probably the best representation in terms of showing the delocalized electrons. So in terms of how in this enolate, how the electrons might delocalize. Well, you might imagine there's a pi orbital on the carbon, a pi orbital on the oxygen, these are overlapping to form a pi bond, but there's also probably a pi orbital here. If you learn about hybridization, you'll find out more about that. And so actually, the electrons are delocalized across these three atoms, this carbon here, and this oxygen here. So if you study resonance forms, you know it's quite simple. We can just draw these arrows and say the resonance form is this, with a negative charge on the oxygen. But what this really means, and maybe how you might work it out if you're a bit more unsure about resonance forms, is that it's really a hybrid of these two structures. So there's this partial negative charge on this oxygen here, partial negative charge on this carbon here. Obviously oxygen is much more electronegative than carbon, so this is going to be by far the bigger delta minus. But there's also a delta minus on this carbon, which proves to be quite important. And there's also partial double bond character. But I think for this question, in terms of drawing a resonance form rather than a resonance hybrid, which is what I call the thing I just rubbed out, I think this is probably the resonance form you want to draw here. So that's our answer to part C. Part D, take the correct statements about the reaction between iodomethane and the enolate intermediate. So the first one's talking about a redox. Well, if we take this molecule here and we assign oxidation states, well, most electronegativity tables, measures of electronegativity, have iodine being the more electronegative. So if we were to assign oxidation states, we'd have iodine in the -1 oxidation states. And then when we break this bond, because we're doing effectively a nucleophilic substitution reaction here, so this carbon's going to attack this carbon, we're forming this and also I minus. And then here, the I minus is also in the -1 oxidation state, so no redoxes happen. There are some tables which have iodine being less electronegative than carbon, so effectively you had something like this, but I don't think we should worry about that. And they weren't expecting you to take either of these statements. I think the easiest thing to say here is no redoxes actually happened, so we're going to cross out both of these. Next, talking about electrophiles and nucleophiles. Well, I just drew out the mechanism for this reaction, and I hope you can agree that this is definitely donating an electron pair from a negative charge, so this is going to be a nucleophile, and this is accepting the electron pair, so this is the electrophile. So the enolate intermediate acts as a nucleophile, and the iodomethane acts as an electrophile. Last, acids and bases. Well, the most common definition at A-level for acids and bases are the Bronsted definitions. So the Bronsted definitions, the Bronsted-Lowry definitions, involve accepting or donating H+. Clearly that doesn't happen here if I draw out the mechanism again. There's definitely no H+ involved here, so that doesn't happen. There is another definition of acids and bases called the Lewis definition. A Lewis acid contains basically an empty orbital, and with this empty orbital, for example, if we say this one's not empty, if there's another a lone pair of electrons somewhere, it can donate into this empty orbital, and we call the thing that's donating the lone pair of electrons a Lewis base, and the thing accepting the electrons into its empty orbital a Lewis acid. In this case, you wouldn't really say that the iodomethane has an empty orbital. Obviously, the enolate does have a lone pair of electrons which is donating, but we wouldn't really say the iodomethane has an empty orbital. Really, it's the antibonding orbital which is accepting the electrons here, if you know about that. But we wouldn't say that the iodomethane is acting as a Lewis acid, so we can rule out these two as well. So that's our correct answer, is the nucleophile electrophile one. Part E, draw a structure of compound A which is formed as an intermediate in this reaction. Well, I hope you can agree, well, we just discussed here that the enolate is a nucleophile. So this is our nucleophile, and we've got a carbonyl compound. You might have studied some reactions of nucleophilic addition to the carbonyl group. We've got a nucleophile here, and we form this kind of tetrahedral product or intermediate, depending on what kind of reaction we're doing. It's exactly the same here. So we've got our nucleophile here. I'm just going to draw the carbonyl compound like this, just to make the whole thing a bit easier to see. And we're going to get that bond here, a new bond here, and then O minus like that. If we look at the molecular formula C6H12O2, well, if we count the number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we need another one, so the obvious choice is we're going to protonate this oxygen to form A as this molecule here. Now we're on to the organic synthesis part. This is pretty tricky. It definitely involves a bit of extra reading if you want to get full marks here. But we can definitely make a good stab at some of the questions just from what we've been taught here about enolates, and especially deprotonating the alpha position. Firstly, we're starting off with this molecule, some ketone and an alcohol, and we're treating it with HCl. I think important here is to look at the molecular formulae. If we look at this, we see we've only got one oxygen and a chlorine in molecule B. So we know, well, one of the oxygens is going to be lost. And if we count the number of hydrogens as well, you've got 3 here, 5, 7, 9, 10. We've lost the hydrogen as well. So I think it's fairly obvious that this hydroxyl group has been replaced by a chlorine atom. So we're going to have B as being this molecule here. Probably some nucleophilic substitution reaction where HCl is a source of chloride ions, and that's going to do nucleophilic substitution on the carbon next to the hydroxyl group. Now, step 2, making a molecule C. Well, we've got a base here. I think potassium carbonate is pretty well known base. And what were we told about carbonyl compounds? Well, if you remember, here I said this would be quite important. We're saying the carbon next to a carbonyl group, i.e. in the alpha position, is deprotonated. So we've got 2 alpha carbons here, and we've got a base. So one of these is going to get deprotonated. The question is which one? Well, if we consider the hydrogens here, which draw 1 each, we have this chlorine atom here, and chlorine's electron withdrawing is electronegative. So if we draw out the 2 structures that we get after deprotonating, we get this one if we deprotonate in this position, or we get this one if we deprotonated in the left position. And this one's going to be slightly more stable because we've got this concentrated negative charge here. Yes, it can delocalize onto the oxygen. Sorry, I drew that badly. But also we've got this chlorine here, which is closer to the negative charge, and that's going to help suck some electrons away effectively through what I call an inductive effect. So this one here, I've ringed in purple, is the more likely, I think, to form. So we've now deprotonated. And now effectively what we've got is a nucleophile and an electrophile in the same molecule, because this carbon is going to be quite electrophilic next to a chlorine. So we might expect something like this to happen in an SN2 like reaction, a nucleophilic substitution reaction. If we draw out what we form from this, it's going to be a 3-membered ring. And that's always encouraging because we've got a bunch of 3-membered rings in our product. So this is going to be our compound C. Now we're going to look at step 3, converting C into D. This is where things get really quite tricky, I think. So this is compound C. And again, what are we reacting it with? Well, this is a pretty weird way of representing this molecule, actually. But if we draw it out, well, we've got Al3 plus ions, basically, and a 1 minus anion. So 3 of these 1 minus anions. So what is the anion? Well, we've got a carbon, we've got 3 methyl groups attached to it, and then we've got an oxygen. And so our negative charge is going to be on the oxygen. And effectively what we're saying, we've got 3 of these and an Al3 plus. So this is the compound we're forming. Now, this is quite a strong base because it's got this negative charge on this oxygen. So again, we're looking at deprotonating things. So this base is actually famous enough. It's got a name. It's called tert-butyl oxide. I'm going to write it like that just to save some space. But effectively, we've got this negative charge on the oxygen, which is going to be quite happy to deprotonate stuff. Again, we've got a choice because there's 2 alpha carbons. Which one are you going to deprotonate this time? Well, this time, if we draw out the products of deprotonation, we could form, again, on the left-hand carbon, having the negative charge on deprotonating the left-hand carbon, or we could deprotonate the right-hand one here. And you might know that carbanions have the opposite stability trend to carbocations. So carbocations are most stable when they're tertiary and least stable when they're primary or methyl. And it's the opposite for carbanions because they're already electron rich, so they don't need more of these inductively electron donating alkyl groups. So the top one's actually going to be more stable here. So this is probably what we're going to form. Now, so if we draw out the mechanism, we have to draw out, that's what we're going to form. And now this is a nucleophile. Do we have any electrophiles we can react it with? Well, yes, we do, because we've actually got more of a starting material. And this is a good electrophile because we've got this polarized C-double bond. And so this is probably going to attack this electrophilic carbon here. And if we draw out the product from this, we're going to get something fairly complicated. So I'm just going to draw out the bottom molecule first, and then draw out the top one. So we're forming a new bond to a carbon bonded to a carbonyl group. So, and then that's got something like that. So this is what we're forming basically. And you might think this will accept a proton, and it probably will. So let's just draw this as OH from somewhere or another. You can check the molecular formula of this compound with the one they've given us for compound D. And you might notice there's only one oxygen left in compound D. So this can't be our final product. So something else might happen. And again, I refer you back to what they've told us. Alpha position carbon, the alpha carbon getting deprotonated. We still got more of a strong base lying around. So we're probably going to deprotonate an alpha carbon again. And yes, for the same reasons, we're going to deprotonate this hydrogen here instead of this one. In this case, probably because of a mixture of things, there's an inductive effect from this OH group. There's two hydrogens here as opposed to one. So the hydrogen here, the hydrogens I've left are probably the most likely to be deprotonated. So this carbon here is probably most likely to get deprotonated. We've got more of a strong base lying around. Probably going to deprotonate the hydrogen. And this is going to be some sort of elimination reaction here. Probably not in one step like I've drawn it, but just for simplicity, we're going to form an alkene from this, which looks like that. So if I draw out this mechanism a bit more neatly, you might see what's going on. So this probably doesn't all happen in one step. If you're interested about elimination reaction mechanisms, you can read Claydon, which is a great organic chemistry book, and I'm going to mention again in a second. This is probably going to be our final molecule here. If you check the molecular formula with what they've given us, I can tell you that they're going to be the same. So this is compound D here. Now, the next part is really, very tricky indeed. Step 4 involves treating this compound D with hydrazine, which is this molecule here. And there's no real way to be able to get to the correct answer, the fully correct answer, without reading a bit more chemistry well beyond the A-level syllabus, I think. So this is something, what's going to happen here is something called conjugate addition. The reason this happens is because we've got an alkene adjacent to a carbonyl group. And effectively what this means is that this alkene is also quite electrophilic. So effectively the first nucleophilic attack of the nucleophile, obviously we've got a good nucleophile here in hydrazine, is going to take place of this carbon. Now I'm not even sure this is the correct mechanism. I'm not sure about any of this really. I'm just trying to give what I think and how I would probably do these problems, so do correct me if anyone's got better ideas. But yes, so if you want to read more about conjugate addition, this is in Claydon. This is in chapter 22 of Claydon. I recommend reading pages 498 to 504 if you have a copy. So what this means is the first nucleophilic attack could very well happen at this alkene carbon that I just mentioned, which is the rest of the structure. Our nucleophile, which is hydrazine, could attack here, and then we need to move these electrons around. So one way of representing this is through a kind of enolate intermediate, although the fact that it's an enolate proves to not be very important. So this actually has a positive charge. We've got a double bond here now. That's the first kind of intermediate, I guess. May very well not actually be an intermediate that we form. And then I'm just going to say there's some proton exchanges happening. So there's going to be some kind of base which can accept a proton off this nitrogen here, whether it's a base, it's a conjugate base of a solvent, whatever. And then some acid here, which, sorry, not A, H+, of course. And that's going to donate a proton to this negative oxygen. So if I just write this as plus minus H+, because we're not really being tested on mechanism. If we were, we'd have to draw out probably all the arrows of that happening. I'm just going to say, well, this happens. And then we form this kind of intermediate, effectively. And then some of you might know this is an enol, and enols are tautomer as a keto, so keto enol tautomerism. So actually, what would happen more likely is something like this, and then this alkene actually accepting an H plus rather than this oxygen accepting an H plus. And so the keto tautomer kind of dominates actually. So another plus minus H plus, which is actually more likely, probably is still NH here, NH2, but instead of forming an enol, we're going to form a carbonyl ketone. And so these two are in equilibrium with each other. The bottom one is much more favoured. Keto enol tautomerism. Another topic you might want to read about. I think it was in some previous Olympiad papers, so they do cover it quite well. Now, we've got a nucleophile, this nitrogen here, an electrophilic carbon, which is polarised by the C-double-O bond. So we got an amine and a carbonyl. Something a bit more commonly tested actually on Olympiad papers is imine formation. So this is just basically going to be a standard imine formation now. So if we draw out the product of this, imine formation will also be in Claydon probably, but you also might know about it already. So we form this, and then another proton exchange. I'm not even going to draw it out. I'm not even going to write plus minus H plus this time. I'm just going to be very lazy and say this. And then what happens is an elimination effectively to form the imine. So a low pair of electrons goes into that, forms a pi bond, and then we lose this hydroxide group. Maybe it's protonated actually as a leaving group, but it doesn't really matter. We're not being tested on mechanism. This is just a way for us to find the correct product. And then this will form this. Yes, and this is what we'll form, and we'll lose this hydrogen probably. And then if we compare this to the molecular formula we're given, well, C10H16N2, you can trust me, this is correct. So this is our compound E, which is really very tricky indeed. Not really sure how they expected people to get this. They did allow 1 mark if you just added, so where's my compound D? If you just added hydrazine to this carbonyl at a normal imine formation, you form something called a hydrazone like this, and they did allow 1 mark for that. That matches the molecular formula, so you got 1 mark for that. But this is the fully correct answer. Now, how we get from this to this, I honestly have no clue, but we'll trust that it happens. So this is question F, part I. Compounds B to E. Part 2, tick which steps involve enolate chemistry. Well, step 1, we formed this alkyl chloride. No enolate chemistry there. Step 2, well, we've drawn out step 2. This definitely does involve enolate chemistry. We've got an enolate intermediate here, sorry. And that is acting as a nucleophile, displacing our chlorine atom. So that definitely involves enolate chemistry. So step 2 definitely does. Step 3, again, we formed this enolate here, which then attacked another molecule of compound C. Definitely involves enolate chemistry. Step 4, well, we did kind of form an enolate intermediate here, but we didn't really do anything with that. We just had a nucleophile attacking the carbonyl group. That's not enolate chemistry, so it's only step 2 and step 3. Now, question G, tick the reaction type catalysed by enzyme 2 in the answer booklet. Again, I wouldn't recommend you read this because it's just a waste of time, and this exam is pretty time pressured. If you're interested, go back and read it after. So tick the reaction type catalysed by enzyme 2 in the answer booklet. Enzyme 2 will be doing this reaction here. What's changed? Well, we changed this carbonyl group to an alcohol. Should be able to recognise that as reduction. An easy way of spotting these things is how many bonds are we forming to electronegative elements. So this X could be oxygen, could be a halogen like bromine, chlorine, could be nitrogen. How many bonds of those types do we have? So in here we have 2. Here we have 1. On this carbon, I mean, not in total. On this carbon, so that's definitely a reduction. Identify the other products X and Y of enzyme 3. This is pretty tricky, I think. Effectively, we just want to find a way we can get from these 2 molecules to here. Now, this is just a guess, really, as to how this might happen. And then we'll see what byproducts we come up with. So, what I'm thinking here is we've got a dicarbon in our compound. This hydrogen here is going to be quite acidic, or relatively acidic. So I think a reasonable first step that might happen is we deprotonate it and we form this enolate-like nucleophile. And we've got a thioester here, I think they're called. Well, it's an ester, but apart from one of the oxygens has been replaced by sulfur. That makes it more electrophilic, actually, because the sulfur is a poorer donor into that carbon, so it makes it more electron deficient. So I think this is a plausible first step. Again, I have no idea whether this actually happens, or if this is even how they were expecting people to do this question. I just don't really see how you can do this question otherwise, without trying to do at least something. So this is going to form, oops, and then our oxygen here, our O minus, and then we might eliminate this sulfur leaving group. I think that's fairly reasonable. We can't really eliminate much else. We're not going to eliminate this methyl group, so now we're going to form this. And we formed a sulfide kind of thing. Not sure if I can call it sulfides actually. What might happen here? Well, we've got an acid. This is going to be a okay-ish base, not a great base, but okay. So we might deprotonate this carboxylic acid here. So we might actually form that. And then, well, what happens from here? Well, if we look at where we want to get to, we want to get to this. I'm actually going to draw it out even. This is what we want to get to. The entire point is we're trying to find a way we can get to this molecule here. If we look at what we've got, we're basically there already, because this part is just what I've drawn in red. So we need to get rid of basically this part of the molecule. And if you actually look at it carefully, and we draw some arrows in, when we do that, we're actually forming this here, which you might know is carbon dioxide. And the other product we're going to form from this is almost our desired product. If there's an H plus lying around somewhere, that is our desired product. So we formed these two things, HS thing and CO2. If we look at what we've been given, X and Y, we can judge that X is CO2 and Y is HS, like we have here. Again, I don't know if this is correct, but this is the way that I can see we get to this molecule, which is what you have to try and do if you want to figure this out. Lastly, complete the table in the answer booklet to give the order of the enzymes required for this process. This is actually fairly straightforward once you've got your head around everything, because this is what we're starting with. You can see that this is exactly the same as the starting materials for enzyme 3. So that must go first. What goes after that? Well, we created this, produced this rather, probably. That's the material that enzyme 2 needs to work on. So enzyme 2 is going to go next. Create this. This is what enzyme 4 needs. So enzyme 4 is going to go after that. And lastly, we're going to have enzyme 1. And then that final product should be the same thing we have it, and it is. So the order is firstly enzyme 3, then 2, then 4, then 1, and that's the answer. Thanks. Hopefully you found this useful. Not very experienced in making videos, so yeah. If you have any better ideas or you think my chemistry is wrong, please do tell me. I'm always happy to learn. I am a chemistry student, so I really actually want to learn a lot more about chemistry. So okay, see you next time. Bye.